hold on.
Oh boy. All right. We're waiting for the stuff to get, and we're gonna. All right. Are there any questions as I start getting stuff pulled together here? Anything that you want to see done? Question? Yeah.
How accurate do you want all the algebra to be? Because I feel like how many points kind of are you going to take off for a wrong answer when like all the steps are there? But I just feel like it would take me a long time to make sure every algebra step.
So on something like, one of the quizzes, 10-point quiz with one question on it, normally what you're going to see is something in the neighborhood of about 8 points for the analysis and 2 points for the correct numerical answer. On a 5-point question, it would be something more like 4 points for the analysis, 1 point for the answer. So something like that. So, and I don't know that I'd ever go much higher than that either. So even if on the exam I were to write like a 20-point question, then it'd still be like 18 points for the analysis and 2 points on the math. Because it's really easy to screw up the math, and it's actually pretty hard for me to grade the math part too. And it's much easier for me to just look and say, all right, you wrote all the equations out properly and you got a weird answer. And unlike the good people in chemistry and physics, I also don't particularly care about significant figures. So I'm not going to be real picky if your answer is not exactly the same as mine either. I know just grading the quiz this morning for the online students, the answer I got was something like 0.76 milliwatts. And there were some 0.754s and some 0.77s, and it's like, yeah, you got the answer, you just rounded differently. So, any other questions like that? In the way of kind of announcement type things, I did send out an email last night that, again, I won't be in my office. I wasn't in my office this morning because they're waxing half of the second floor of the Ark. I won't be in my office tomorrow morning for the same reason. So you'll just have to. I will be there for the rest of the day. So if you have questions, you can stop by then. We do have an exam coming up on Thursday. I'm going to reserve the room for that today, and I will email you guys, let you know where it's going to be. It should be at 6 o'clock and I'll reserve the room from 6 until 7:30 on Thursday. Probably shoot for some room on the second floor of the Ark. So we'll give you an hour and a half to work on it. You can take as much or as little of that as you want. What I will do is I will write the exam to take as long as I would normally take for an hour-long exam, and you'll have an hour and a half to work on it. So plenty of time to check your work. And I'm not going to find what I'm looking for in all of this EE 2171 stuff. I'm not going to find the lectures I'm looking for, so I can stop doing that. I guess another announcement, at least one person pointed out that some of the numeric answers that I got during the nodal analysis lecture were not right. I just was relying on my notes to give me the answers, and I wasn't actually calculating them. So if your answers differed from mine, that's probably okay. You probably have, because I think most of the answers should work out to be nice and round numbers as opposed to some of the weirder fractions that I got. So, okay, we're getting close to being able to start. So what you should expect to see in terms of the schedule for this week then would be we'll finish up node analysis today, or node mesh analysis. The only thing left to really take a look at is how to deal with shared current sources. in terms of what we call a super mesh. That's really the only thing that's left to do. And yeah. And then we'll move on to something called Thevenin and Norton analysis. With Thevenin and Norton analysis, what we're doing is we're trying to simplify all of our circuits down to something that's just basically two resistors and either a voltage source or a current source. Makes analyzing the circuit a lot easier. So, and just to review the stuff that we talked about for mesh analysis, basically what we're going to try to do is we're going to try to quantify, we're going to introduce these analysis currents, these branch currents or mesh currents, whatever you want to call them, that allow us to, at any point in the circuit, quantify the actual current in terms of these analysis currents. And these analysis currents don't really exist in the circuit. They're just a tool that we use to get at the answer. And so it's based on KVL as opposed to the nodal analysis being revolving around KCL. And so we'll get another simultaneous sequence or set of equations, and then we'll solve for all of the various equations as necessary. We'll solve those equations and it'll give us the parameters as we want them. So one thing that's important to, again, differentiate just a little bit is the difference between a loop and a mesh. A loop is a path where you only meet that node once. A mesh is a loop that contains no other subloops, and we looked at least a small picture of that. We can quantify all of the real currents, and this slide goes with a diagram that had a bunch of different currents flowing around in them. And all of the, I think the I sub A, I sub B, I sub C, I sub D are the analysis mesh currents that we've introduced as to figure out what's going on in the circuit. And we can easily quantify all of the real currents in each of the branches in terms of our analysis mesh currents. The fancy way of quantifying the number of equations we'll need is this b minus n plus 1. Realistically, you're going to kind of look at it and see it like a window, and the number of panes of glass that are in that window tell you how many equations you're going to have to write. What is nice about most of these mesh analysis is you get somewhat more compact or easy, friendly looking equations as opposed to all of the fractions that you see in nodal analysis. So after you write the equations, you just solve them and you get your answer. It's not too bad. I did a number of examples of that. And with voltage sources, it's all very easy. And regardless of whether it's a dependent source or an independent source, again, with the dependent source, it's always just going to be, we write the original KVL equations as if that dependent source was independent, so that, you know, if it was a 3Vx voltage source, you just, in your KVL equation, you write plus 3Vx or minus 3Vx, depending on which terminal you ran into first. But current sources can be easy, they can be hard. In the event that only one of your mesh currents, your analysis currents, is going through that current source, it's really, really easy, because you want to know what that current is. Well, it's whatever the current source is putting out, and that's period the end. That's just how it works. When you have two branch currents or two loop currents that would be going through the same source, that gets a little bit harder. So we can take a look at some examples. I don't remember, did I do an example that had a dependent current source in it anywhere? Or I don't think that I did, but we did that one. And okay, so this is kind of where we're at. All right, so this is the circuit. I think this was the last thing that I drew on during that pre-tape lecture. We've got this circuit. Got a nice voltage source up here, resistor, current source, resistor, resistor. 6 volts at that source, 1K at this source, 1K, 4 mils, 2K, 2K, 2 mils. So here's our circuit. The analysis, or the currents that we're going to introduce here, we're going to say, well, that's I1, and that's nice because it's constrained to the 2 milliamps. We don't have anything weird to do there. Define this current, call that one I2, also constrained by the 4 milliamp source. Beautiful, beautiful thing. It's awesome. Makes our analysis easy. So I1 is simply 2 milliamps. I2 is simply 4 milliamps. But what do we do about this next one? We know we can look at this and we say, well, there's 3 equations that we need. But what do we do about that third equation? Because what we kind of naturally want to do is to run a branch current around here, a loop current around here. But that would basically say, well, then this is negative 4 milliamps. But that's not really the case because we have this current source that's already tied to this loop current. So we have to go around the current source in some way. And there's a couple of different ways that we can think about doing that. And what they all essentially give you, both of them essentially give you the same answer. The first is to say, let's open circuit this current source. In other words, rip it out and create a loop that goes around the circuit without that current source in it. So let's visualize what that circuit looks like, and I'll skip the circuit parameters just for time's sake. But so we've got the voltage source, the resistor, current source. Here's where the current source was, and so we'll just yank it out, leave it open circuited, and now we've already defined our loop. First loop current is going around like this, our second one like that, and so now we just need to we're going to go around this loop and come down here and back up and around, and that will complete our loop. And we create that loop again by open circuiting the problematic current source. What you have to be very careful about then is recognizing that in this resistor we have a current I2 and a current I3, and they're going the same direction through that particular resistor as we've defined them going through. In this resistor's got a whole bunch of currents running through it. It's got I1 flowing in one direction. It's got I2 and I3 flowing the same direction. So it kind of doesn't matter a ton how you quantify that, just as long as you recognize that all 3 of the currents are running through this particular resistor, and two of them are flowing the same direction. One of them is flowing the opposite direction. So let's go back to our circuit, the full-blown version of the circuit, and start writing our mesh equations, considering that this is how we're going to get around this third loop. So we've already kind of written the first equation, or the first 2 equations are just constrained by the current source. So we just write the one equation for our loop I3, which is this last current that kind of goes around in a funny way. And we can say, all right, we've got negative 6 volts. We run into the 1K resistor that just has I3 running through it, so that's 1K times I3. Now we come down here, we're in the 2K resistor. We have 2K. Now I1 and I2 are both running through this resistor in the same direction, so it's I2 plus I3. Come around the bottom, nothing there. Now we get to this 2K resistor, and again, I want to put the resistor that I'm in, or the current that I'm working on, I'm going to put that one first in my analysis when I write out my term. So I've got the 2K resistor. I3 is my point of reference, and I3 and I2 are running the same direction. So that's just going to be I3 plus I2. And then I1 is running the opposite direction, so we'll say minus I1. The last one is the 1K resistor. We've got the 1 kilo ohm of resistance times, in this case, we just have the two currents, I3 and I1, that are going through that. So I3 minus I1. That brings us back to where we started. That equals 0. So we can go ahead and we could substitute in all of the numbers. Why don't we go ahead and do that? So try to simplify all the I3s because that's the only variable that we're really left with. At 1K I3, 3K, 5K, 6K times I3. We've got, let's see, 2K times I2. That's going to give us 8. We've got 2K times I2 for another 8. And then 2K times a negative I1, so that'll give us negative 4. And then another negative 1K times 2, or just, that should be negative 2. Minus 6 equals 0. So that's, this is the same negative 6 here. So that's 16, 10, 4, if I add those up correctly. Or at least a negative 4, 16, and negative 12, just positive 12, positive 10, positive 4. So that goes over into the other side. 6K times I3 equals a negative 4, negative 6, positive. Well, we had 16 and then minus 4, so that's positive 12. Now I'm confused. 16 minus 12, yeah. So it was a positive 4 on one side. When we put it onto the negative side, on the other side, it'll be negative 4. Divide by 6K. Divide by 6K. So I3 equals negative 2/3 of a milliamp. And so, now you have all three of your loop currents. And you can figure out anything else. If, for example, you wanted to find out the voltage, and we'll call that V0 across that 2K resistor, you'd have to bear in mind all of these values as you've defined them so that you can properly figure out what's going on. And make sure that you pull all three of them into that final term. So that's one way to do it. The other way to do it is something that we kind of call a super mesh. And the idea here is that the circuit, what we're going to do is we're going to kind of ignore the fact that there was a shared current source, and we're just going to define all of the currents the same way that we would normally. And we're just going to run into a bit of a bit of a wrinkle in the way that we do it, because we need to know what the voltage is across the current source. So again, here's what our circuit looked like to start with. So 2K of resistance, 2K of resistance, 2 milliamps, 1K, 4 milliamps, 1K, 6 volts. So we'll define I1 and I2 exactly the same way so that they coincide with the the current sources. And then we're just going to go ahead and we're going to define I3 as going around the top loop in just the same way we normally would, and say that's I3. But what we can't do is just say, well, it's flowing the opposite direction as the current source, so it's negative 4 amps. We can't do that. What we're going to do is we're going to introduce a voltage and just write a KVL equation around that source, and we'll call it Vx just for so that it's consistent with the notes. I don't know if I actually put this stuff on there. Yeah. So these are the slides that correspond with that. But so what we do is we introduce a voltage Vx across that current source, and now we can write our third equation just going around the outside of the loop, but we'll include this term for Vx as the voltage across that particular source. So we run into the negative 6 volts of that. We've got 1K times I3. We've got this voltage Vx that we ran into, and then we've got 1K times I3 minus I1, and that equals 0. But what we need to figure out is what is Vx? What is that particular voltage? How do we even solve for it? The thing to remember here is that elements in parallel have the same voltage across them. So what is in parallel with this 4 milliamp current source? Well, it's this 2 kilo ohm resistor and this 2 kilo ohm resistor. So we can say, well, Vx equals 2K I2, and we've got yeah, I think this is right. And then 2K times I2 minus I1, I think. I think that's right. And once you've done that, you've essentially done the same thing. You should end up running through the same, getting the same answers when you plug that back into your equation. And this way I don't like nearly as much. Basically what I like to do is just find a path that doesn't include that current source. So I will almost always personally do it this way and say, look, I'm just going to find a path around that current source that doesn't include, that just doesn't include the current source that's being a problem, and write the equations appropriately. So this one looks a little too easy, but don't I have a good example of a... Boy, what I wouldn't give for a good example of a current source. Let's see if we can kind of make one up on the fly. This is always dangerous, but I want to do at least one more kind of super mesh example. So let's say voltage source, resistor, resistor, current source, resistor, and let's even say we have another voltage source over here. Okay, so say this is a 6-volt source, this is a 3-volt source, and the numbers on this will probably not work out real nicely, but I'm just going to call them all, say, 3 kilo ohm resistors. And that this is a 6 milliamp source. Since this is totally made up, this may not have a really nice answer to it. But in this case, the first thing that you should do is look at this and say, well, I would like at least one of my loop currents to, we know that we need 3 equations to solve this circuit because there are 3 panes in it, 1, 2, 3. And I'd like at least one of my loop currents to do a good job with this, this 6 milliamp source. So let's just write this one as being nice and simple. That's I1. I2 comes around here so that it corresponds directly with the direction of the 6 milliamp source, and we can right away say that I2 equals 6 milliamps. But we can't, again, the way that I would encourage you to do this and the way that I like to do it personally is not to define I3 as flowing around this loop, but just to find a different loop for it to go around. And essentially, You have, I guess, two options. You can have it go around just this part of the circuit, the right-hand two panes, or you could go all the way around the outside of the circuit. And as long as you're consistent, it shouldn't matter, and you should get the same answer either way. So I don't think it matters a ton either way. We have to run into 3 resistors. So let's just take it all the way around the outside of the circuit. Come back around, and that will be our I3. So we're staying out of the way of that 6 milliamp source. So writing our equations for this is going to be, we have to be very careful about what we do on these other 2 equations, and remember where I3 is in the circuit as we're going through. So the first loop for I1, we've got the negative 6 volt source. Then we've got the 3K resistor that I1 is flowing through, I3 is also flowing through, and they're going the same direction. So we'll have 3K times I1 plus I3. Then we get down to this 3K resistor down here. That one's going to have the 3K. It's got I1 running through its one direction, I2 running through it the other direction, which is a negative, what would be a negative 6 milliamps. And so that's our first equation. The second equation, going all the way around the outside of the circuit, say we start at the 3 volt source, come around here, we run into the 6 volt source at the negative terminal. We've got the 3K resistor, and just for consistency's sake, we'll say, all right, well that's I1 plus I3, so these are the same voltages. It's the same thing. Then we get to this 3K resistor. Again, I3 and I2 are flowing the same direction through that resistor, so we'll sum those currents. That'll be I3 plus 6 milliamps. And then this 3K resistor in the far right pane just has I3 running through it, so it'll be 3K, I3, and that sums to 0. So now you've got your 2 equations, you've got 2 unknowns, and you can solve for what I2 and I3 are. Let's do that at least kind of quickly. Let's see what I can do. So we've got 2 constants here. The 3K and the negative 6 milliamps will give us a negative 18 and a negative 26. We'll put 24 on the right-hand side of the first equation. And we've got 6K I1 and a positive 3K I3. And that's our first equation. The second equation here, we've got positive 3. This will end up being a negative 3 after that negative 6. And then this gives us a, again, a positive 18. So we had a negative 3, positive 18, which will give us a negative 15 on the right-hand side. We've got positive 3K I3, sorry, positive 3K I1, and 6K I3. I have to run over to my bag to find my calculator, but it shouldn't be too bad. I guess picking multiples of 3 works nicely. So, 2 equations, 2 unknowns. Simultaneous, 2 equations, 6,000, 3,000, 24, 3,000, 6,000, negative 15. So what I get is that I1 equals 7 milliamps, and let's see, so we got I3, so we got, yes, thank you. So that should be a 9K. So those are all K. And make this a 9K. Whoops, 9,000. So that makes the numbers a little less nice. I get I1 equals, I guess, 5.8 milliamps. and I3 equals negative 3.6 milliamps. And still, I2 is 6 milliamps. So that's, you should be able to get the same answer even if you were to take I3 and just come back up around and do the two right-hand panes. You just have to remember that in these resistors, you're going to be running into two different currents. And as long as you're consistent with how you write the equations, it shouldn't matter where you actually send those equations to. So that is dealing with those nasty current sources. Apparently, things are in a slightly different order than I thought in terms of the lecture material, because now we look at dependent current sources, or dependent sources in general. So, okay, so we'll look at a couple of circuits that have some dependent sources in them. We'll do a couple of those, and that should get you in a position so you can finish off the homework entirely. All right, so again, the way that we're always going to attack these dependent source circuits is to originally write the equations as if those dependent sources were independent and then kind of sort it all out later. So here's going to be our analysis circuit. This is a 6 kiloohm source. This is a 3 volt source, 4 kiloohm source, a 2K source, and a 2Vx source. And the voltage Vx is this voltage across the 4K resistor. And one of the things that we're going to do here, essentially what we want to solve for, we're going to call it V0, is the voltage across the 6K resistor. What we want to do, we're going to do something kind of weird, and this is suggested by the book, which is to say, all right, I would like my first loop to come around this way, and I1, and then I'm going to send my second loop. It's going to start in the same location and go all the way around. What makes that a good idea, although not necessarily something you might think of right off the bat, is that both of the things that we would need to solve for or write equations for are Vx and V0, and Vx is now determined in just one current. If you were to do it, put I1 here, I2 here, then Vx would be defined in terms of two currents. And all this does is makes the math marginally easier if you do it this way. But so just start writing the equations like it was a normal mesh or loop analysis. We run into the negative 2 volt source, 2Vx source, 2K resistor that has I1 and I2 running the same direction through it. And then I1 comes back down here as 4K times I1. That equals 0. You could. If you wanted to, you could stick that in there. I think in general, what I like to do when I'm solving these kinds of things is to get rid of the unknowns instead of writing this one in terms of Vx, but you could do that if you wanted to, and to simplify the original equation. So go around the loop for I2. The first couple of terms are going to be exactly the same because they run through the same circuit elements. And here's where we have the departure, is that I1 goes down through this branch, I2 comes through these last two elements. We've got the 3 volt source, and then we've got I2 times the 6K resistor, and that equals 0. So those are our first two equations. Unfortunately, we've got three unknowns at the moment, so we need to write an equation for our controlling parameter in terms of a circuit element Vx equals just 4k times I1. So now you can take this information and substitute it back up into these two equations and get you down to two equations, two unknowns, and off you go. So you can solve this one the rest of the way just for, I guess, for kicks. We've got the two equations. When we substitute stuff in for equation 1, we'll get negative 8k times I1. That's replacing the Vx in this term, plus 2k I1 plus 2k I2 plus 4k I1 equals 0. And so that's negative 6k I1, negative 2k I1, and a positive 2k I2 equals 0. The second equation, again, the first few terms will be the same, negative 8k times I1 plus 2k I1 plus 2k I2 minus 3 plus 6k I2 equals 0. So on the right-hand side, we'll have the 3. Again, we've got negative 8k I1, negative 6k I1. That's the only terms for I1 we've got, negative 6k I1. And then we've got positive 2k I2, positive 6k I2, which gives us a total of 8k I2. So we can solve those simultaneously. Two equations, negative 2000, 2000, 0, negative 6000, 8003. And what we get are both I1 and I2 are, I guess that's 1.5 milliamps. And that's what happens when you do an example problem out of the book, is you get nice numbers. Same thing happens when you see a current source. Let's just do one last kind of interesting problem and call all of this stuff done. So here's kind of one problem that puts all of the loop analysis stuff together, and should put us in a position where there's not at least some aspect of a homework problem that you haven't seen. Now, if this isn't the most horribly contrived problem in the world, I don't know what is. We have one of each kind of source. We've got dependent voltage, independent current, dependent current. This is a 4 milliamp constant source. This one is defined in terms of, it's 1/2000th of whatever Vx is, and Vx is defined as the voltage across this 2 kilo ohm resistor. This is a 2K resistor up here as well. This one is a 1K resistor. This one's also 1 kilo ohm. This dependent source is 1000 times Ix, where Ix is the current through the 1K resistor. And then this is a nice simple 12 volt source. So here is our ridiculousness, but it's a good example circuit that has one of everything in it. So we'll define all of our loop currents. We look at this, we see 4 panes in our circuit, so there's going to be 4 loop currents. I1, I2, I3, and I4. Now 2 of these are going to, again, they're going to be constrained by the current sources that define their loops. So we can say right offhand that I1 just equals 4 milliamps. And we can say that I2 equals Vx over 2000. And we only really have to kind of sort of write real KVL equations for the bottom two panes of our loop, because really the first two are constrained by those current sources. But one of the things that we're going to have to do is come back and write something that defines what this Vx term is in terms of other circuit parameters and in our loop currents in order to be able to solve this completely. So the first equation that we'll write for I3 will look like, we will run into the dependent or the negative terminal of that dependent source, so it's 1000 times Ix. We've got 2000 times I3 minus I1. We've already got a number for I1, so let's stick it in there, 4 milliamps. And then when this 1K resistor has I3 running through it and I4 running through it the opposite way. So that's our first circuit, or first equation. Second equation will look, I think, fairly similar, because we've got the 1K resistor times I4 minus I3. I4 is the current we're working with, so we're going to put that one first. Then we've got the 1K resistor that's times I4, and the I2 current that's running through it is Vx over 2K. So that one's kind of nasty enough that I'm just going to say minus I2, and we'll come back and sort that one out later. And then we run into the positive terminal of the 12-volt source, so let's skip a step and say, well, that equals negative 12. So there are some of our equations, but now that we've written our initial mesh equations as if these two dependent sources were independent, now we have to write the controlling equations. I don't know that one is particularly easier than the other, but we look at Vx, and it is a 2K resistor where I3 is running into the positive terminal. So when we write our equation for Vx, we'll say that is 2 kiloohms times I3 minus I1, which is that 4 milliamps. And we can solve that right away. So that's 2K I3 minus 8. So anywhere you see Vx, you can go ahead and you can stick 2K I3 minus 8 in there. So you could stick that in up here. You can stick that in anywhere else that you happen to see it. And since I2 is defined in terms of that Vx, we can stick this 2K I3 minus 8 into this term here. And that will work out. Second thing that we have to write, maybe this one's a little easier, but we need to quantify what Ix is in terms of our circuit parameters. I4 is running, basically it's the current that's running through this 1K resistor, which in terms of our loop currents is I4 minus I2. So anywhere you see this Ix term, you can stick in I4 minus I2. So now we have all of the equations. We've got the equations that describe the behavior of those current sources. We've got the KVL equations around the loops that contain the voltage sources. And then we've got our two nicely simplified controlling equations. And so this is the 8/10ths of the problem that you would be the most heavily graded on. Everything after this is going to be, do you do the math right in terms of getting the right algebra to get this circuit solved. So let's start sticking some of the stuff that we know in there and trying to combine it all. So let's say for our I3 equation up here, we've got Ix in there, so let's substitute that in. So we've got 1K, which is the same 1,000 here, 1K times I4 minus 1K times I2. And that's just substituting this in up here. Then we've got plus 2K I3 minus 8 plus 1K I3 minus 1K I4 equals 0. So collect all the terms together. I only see the 1k I2, and yeah, that's okay. So we're going to have to come back and substitute some information in for I2, but then we've got 3k I3, 3k times I3, and I4 drops out, and then the 8 can go over to the other side, which is positive 8. So one thing we might want to do here is we know what I2 is. It's this Vx over 2k thing, which is, and Vx is 2k times, perhaps in this case, it's a little easier to say, well, Vx is 2k I3 minus 4 milliamps. So if we just, that 2k and this 2k cancel out, so I2 is just I3 minus 4 milliamps. You see where that one's coming from? So say 1k times I3 minus 4 milliamps is getting rid of the I2 thing equals 8. So that means negative 1k I3 plus 4, oops, can't forget that, plus 3k I3 equals 8. So you end up with 2k I3 equals 4, so I3 equals 2 milliamps. And we solved for that without a calculator or anything, just by substituting stuff in. You can do essentially the same thing with I4, just, or this equation that we wrote for I4. Substitute stuff in as you see fit. So let's go ahead and do that real quick. So we had 1k, let's make sure everything's on here. There we go. So we had the 1k I4, we don't have anything to change there, 1k I4 minus 1k I3. And we could, if we wanted to, we've already solved for what I3 is, so we can go ahead and just run with it if we wanted to. Plus 1k times I4. And we multiply the 1k times the negative I2. We figured that I2 was just I3 minus 4 milliamps. So that's plus 1k I3 minus 4 milliamps equals negative 12. So that is negative 1k I3, positive 1k I3, so the I3 drops out of this equation. So we're left with 2k I4, and this gives us a positive 4, and put that over on the other side, that gives us negative 8. So I4 equals negative 4 milliamps, which doesn't correspond at all with the numbers that I got in my that I have in my notes. Did the math seem okay as I was going through? Because I have some fairly different numbers for I3. I just have a different sign on it. I4 is fairly different.
Yeah, and I3 should be negative 1,000 IX here originally.
I know 1 milliamps.
So, which equation?
Yeah,
Up here?
Yeah, that should be a negative right there. Pretty sure, because you're going into a negative from the voltage.
Unless you're drawing back.
Oh, yes, you're right. You're right, very good. And so that would obviously change all of the math that I just spent, 5 minutes doing. So, awesome. So ignore all of that extra work, but the point remains, right? That that's how you're going to solve this kind of problem. You're going to take and you're going to write these equations as if these dependent sources were independent, and that's going to, and then you write your controlling equations, and as long as you write the right controlling equations, you'll get more correct answers. What's that? What the final answers should be are I1, which was constrained by the current source, is 4 milliamps. Once you plug in what you know about I2 and I3, you can, I3 and I4, you can find that I2 is negative 10 milliamps. I3 is a negative 2 milliamps, and that probably is solved directly by the fact that I dropped the negative sign on that voltage source. And then I4 with the changed value of I3 gives us negative 12 milliamps. So, and that's what they should be. I don't, and I'm sure if I hadn't screwed up that one sign, that everything would look much nicer. So. So that's loop analysis. Are you guys feeling comfortable with that? You want me to do any examples or anything? Solve any homework problems?
You can do the hard homework problems if you want.
I'll think about that one. All right, let's sum this one up and take the last few minutes of class to look at some of the stuff that leads us into the Thevenin and Norton analysis stuff. So, summing up all of the stuff for loop analysis, what you're going to do is you're going to find a bunch of loops and you're going to pull them together. And you're going to need essentially one equation for each one of the panes in your window. If all you see are voltage sources, then you don't have anything weird to do, but you don't get any shortcuts either. What you have to do is just write out a KVL equation around each one of the loops, paying attention to which one of your loop currents are passing through each one of those elements. If you do run into a dependent voltage source, then you're going to have to write that controlling equation after, again, you treat it originally like an independent source. If you run into current sources, it could be easy, it could be hard. If just one of your loop currents goes through that current source, the value of that loop current is constrained to the value of the current source. So if it runs through it, and it doesn't matter if that's an independent current source or a dependent current source, it runs through it, it's just going to be whatever the value of the current source is. If you have two loop currents running through it, then you need to essentially find a path around that current source, take and use the current source at least in one sense and say, this particular loop current goes through the current source and I'll grab that and I'll let that constrain that one of the loop currents, and then your last loop current needs to avoid that that current source somehow. Deal with your dependent current sources in the same way, write that controlling equation in terms of other circuit parameters and substitute everything in. Be careful with your signs. So all of these, so these node and mesh analysis are the two original, I guess, kind of most easy, powerful ways to do circuit analysis. And now that we can do loop and node analysis, there's no reason to ever collapse a circuit down to two resistors unless we absolutely needed to. And but what we are going to look at next is essentially an analysis method called these Thevenin and Norton equivalents that do actually reduce a very complicated circuit down to just one source and two resistors for the purposes of simplifying the analysis. Because I think largely the reason for Thevenin and Norton equivalents is that when I write all of these nodal equations or these mesh equations, when I'm done, I just pick up my calculator, start up the simultaneous equation solver, and I can put in 6, 8 equations without any kind of problems. You guys who have maybe the TI-93s or whatever, you'll use your matrix solvers to do the same thing, and you can do that for arbitrarily large circuits. But what you will find is that if you had to do all of those by hand, or if your main tool for solving these things was a slide rule, that might not be so much fun when you have like 4 or 8 equations to try to solve simultaneously. So that's where Thevenin and Norton equivalence and analysis come in handy. But there are a couple of, just to finish this up. So loop analysis is based on KVL, nodal analysis is based on KCL, what I will say now is that at the end of class tomorrow, I'll give you one mesh equation problem to solve as a quiz. And then after that, I will never tell you, solve this as a mesh equation, solve this as a nodal equation. And when we get to the exam on Thursday, there will just be questions, and they'll say, solve for I0, solve for Vx, whatever I happen to pick as the parameter in the circuit, and you choose the method that makes sense for you. And theoretically, as long as you're doing it right, it should not matter. You should get the same answer both ways. And if you don't, you did one of them wrong, because they should give you the same answer. But if you do pick the right one, you'll save yourself some amount of work, because you'll get into, you'll have to write fewer equations, you'll have to write fewer things that do like super meshes or super nodes or whatever. And if you're intelligent about it, you can save yourself a lot of work. So, all right, superposition, linearity, Thevenin and Norton equivalence. So this is one of these, again, circuit analysis techniques that it's just another tool to add to your boxes. Actually, there's 3 different analysis tools that will add to your toolbox for solving circuits. And all of the circuits that we do things with these Thevenin and Norton equivalents, the superposition, the linearity, they're all things that you can do with nodal and mesh analysis. This is just an additional analysis technique. I think largely you see that Norton and Thevenin were designed for when we didn't have computers and PSpice and calculators that could solve big series of simultaneous equations. Before we can get to the Thevenin and Norton equivalence, one of the things that we have to look at these concepts of linearity and superposition. And linearity, I really think is, I'd call it, even in the notes, a little bit of a party trick. So if you go to all of the wrong kinds of parties where you demonstrate your superior circuits knowledge as a main attraction, and I feel sorry for you if that's, even I don't go to those kinds of parties, but you can do that. What we can do with linearity is say, hey, let's say that the parameter that we're looking for is 1 milliamp or it's 1 volt, and then we solve backwards. If that was the case, what would our original voltage had to have been, or original current had to have been? And then we can scale our result. And what that's telling us in the important sense is that circuits are linear. And with that, meaning that if I hook up a 3-volt source to something, and at the far end of a network, I see that there is a 2 milliamps of current. If I were to crank that up to a 12-volt source, or an increase of 4, then I should see 8 milliamps on the far side of the circuit, and a corresponding increase by 4. Superposition is a cool topic because what we can do is we can eliminate all but one of the sources and find out what is the contribution of that source to a given circuit parameter. And once we've kind of figured that out, we can figure out individually for all of the sources what is the contribution of that source to the parameter that we're looking at, sum up those contributions, and that will give us the same answer. And both of those give us kind of a building block to get into Thevenin and Norton equivalence. So again, there are these 2 things that kind of make up linearity, which is additivity and homogeneity. And the additivity is what we'll call superposition in a couple of slides. But the linearity, or the scaling part, says that what I was saying before, that if you double a voltage source, then everything else is going to double all the other parameters in the circuit. So, I mean, assuming that all of the resistances are fixed. So what we can do is we can kind of come up with this goofy original hypothesis that says, hey, what if this circuit happened to be, the voltage that I'm looking to measure was 1 volt, or the current that I was intending to measure was 1 milliamp, or 1 amp. What if that was the case? What would these other circuit parameters have to be, and how does that get us back to where we, to a known circuit value at the source? What does that give us? I don't know, what would that have to be? And the relationship between what we solved for and what the real answer is that we know is the same scaling factor that we'll use to figure out what the real circuit parameter is. So here's an example of this little party trick, whatever you want to think of it as. So here is a simple circuit, and you could analyze this using nodal or mesh analysis if you wanted to. 2 kilo ohms resistance, 4 kilo ohms, 3 kilo ohms, 2 kilo ohms, 12 volts. And so what we want to find out is what is this voltage V out, or what is the voltage across the 2K resistor. Now we could obviously do a quick nodal analysis and say, hey, look, all right, they call this one V1. We could do it, also say here's V2 if we wanted to. Say V1 minus V2 over 4K plus V1 over 3K plus V1 over minus 12 over 2K equals 0. Write the second one, V2 minus V1 over 4K plus V2 over 2K equals 0. Solve those simultaneously. V2 equals V out. That's one way you can do it, right? Or you could write loop equations, figure out what I2 is, and multiply I2 times 2K. That'll give you your V out. We can do both of those. We could also start combining these resistors and say, oh, the 4 and 2 in series can be combined with the 3K in parallel, find out what the current is that's running around the loop, and then do a current divider to figure out how it's going between the two loops. We could do that too. This is just to show you one more way that you could solve this. And that's to say, well, let's assume that V out equals 1. That's going to be our assumption. So if it were the case that V out equals 1, well, let's say that this current here is I2, this one's I1, this is I0. If that was the case, then the current I2 would be the voltage, V out, divided by the resistance of 2K, or it would be 0.5 milliamps. Right? Well, if there's a half milliamp flowing through the 2K resistor, there's also a half milliamp flowing through the 4K resistor. And so that means there's 2 volts across that resistor. Okay? So, let's call it V4K equals the half milliamp times the 4 kilo ohms of resistance for 2 volts. So that means that the total voltage from the node that we marked V1 down to the reference node, or to the bottom here, is going to be the voltage across the 4K resistor plus V out, or 2 plus 1 volts. So we've got 3 volts total at what we marked as being V1. Okay? So that's fine, but what is that, so what? Well, we've got, if V1 is 3 volts across this way, it's also 3 volts across this way. Elements in parallel have the same voltage across them. So the same 3 volts that are across the 4K and the 2K resistor are also across the 3K resistor. Well, what does that mean that the current is that's running through the 3K resistor? Well, I1 equals the 3 volts across the resistor divided by the 3 Ks of resistance. And that is 1 milliamp. So if we had 1 milliamp, if we had 1 milliamp going down this path, and we had 1 or a half milliamp going down this path, that meant that I0 originally equaled 1.5 milliamps. Now if we write a KVL equation around this loop, we should see that 12 volts equals 2K times, well, something, some voltage, let's call it V source, equals 2K times 1.5 milliamps. That's the current that's running through this part. And then we solve for I1 as being, we solve for I1 as being 1 milliamp, but we know that there's 3 volts across this, so it should be 3. And 2K times 1.5 is 3, and plus 3. So what we did is we solved and we said, well, if it were the case that V out was 1 volt, that would mean that the source voltage was 6 volts. But it's not the case that the source voltage is 6 volts, it's 12 volts. And what that means is that V out really equals twice what we figured out, or 2 volts. And why you would ever actually analyze a circuit that way, I can't figure out exactly. It seems very convoluted, but it works, and it demonstrates an important property of the circuits, in that if that was a 6-volt source, that would be 1 volt there, but doubling this doubles that, so on and so forth. So I think when I create the homework assignment, I'll ask you to do one very simple linearity problem, but then you can forget it after that. You don't ever have to use it. If you want to, hey, knock yourself out. Do some linearity problems. And what I have seen people do in the past is figure out, they have actually used superposition in the past to solve some problems on the final exam. And they've used it to good effect. So, may the force be with you. Superposition. This one's a little bit more useful, like I said, because to some extent you can use this whenever you want to, and it's kind of an interesting analysis technique. The basic idea here is that what we're going to do is we're going to appropriately zero out all of the sources except one that we want to figure out what is that source's contribution to the parameter that we're solving for. And once we've appropriately zeroed out all of the other sources, and we go through all of the sources that way, we combine all of their individual contributions, and that gives us the total. Now the key is, how do you appropriately zero out a source? And the answer is that when you are zeroing out a voltage source, it needs to become a short circuit. 0 volts is a short circuit. And that means that you don't just yank it out and leave this big gaping hole in the circuit. There's going to be just a straight line connecting where the voltage source used to be. On the other hand, a 0 amp current source is an open circuit. And so you are just going to go and reach in and grab out that current source and leave a big gaping hole in the circuit, because that would give you 0 amps worth of current. So again, all of the work here is available on the slide if you want to take a look at that. But the circuit that all of that mess is based off of is this guy. And this particular circuit, if you were to look at it as either a nodal or a mesh analysis, would be nasty one way or the other, because either you're going to have a super mesh because of this 2 milliamp current source, or you're going to have a super node because of the 3 volt source. Either way, you're kind of stuck with the analysis techniques that we have, and because what we're solving for is this the voltage across the 6K resistor, it's not really in a position that makes solving using that linearity trick particularly easy. So we have to think up a better way to do it. And so let's try superposition as an example. So let's start out with getting rid of this 3-volt source and find out what is the contribution of the 2 milliamp current source. And again, the way to appropriately zero out this source is to short it out. So there's going to be, these resistors will remain in the same place. We'll have the current source. That'll be the same. And then we just short it out. Goodbye. No more voltage source. This is going to be V0 prime across the 6K resistor. We got 2K here, we got 1K here. 2 milliamps coming out of the source still. Nothing else changes particularly. And probably the easiest way to do this is as a current divider. Say, all right, well, I want to know what the voltage V0 is. Call the current that's running through this I0 prime just to make sure that we keep it straight and don't try to reuse stuff in inappropriate ways. Say, well, I want to know what the current is that's running through the 6K resistor, so that I0 prime will equal some fraction of the 2 milliamp source. We can quickly combine these in series, so we've got 3 over 9, with 3 plus 6 as being our denominator. And so 6/9 is just 2/3. So we got 2/3 of a milliamp is I0 prime. And so the voltage V0 prime will equal 2/3 times 6K, well 2/3 of a milliamp times 6K, which should be 4 volts. So we can kind of set that aside and say we'll come back to that in a minute. So now we need to, so we have the contribution of the current source, now we need to find out the contribution of the voltage source. So we redraw the circuit without the current source in it, appropriately zeroing that out, which means that there's just a hole there. At the voltage source, we got the 6K resistor. This will be V0 double prime to differentiate it. 2K, 1K, and this is 3 volts. So, you know, how can we solve for this one if we want it? So we got lots of options here. I mean, we can combine the 2 and the 1K resistors and do a voltage divider. We could write a KVL equation, solve for the current around the loop. I think the current or the voltage divider is probably the easiest. So say V0 double prime, some fraction of the 3 volts. We've got 6K on the top, and we've got 6, 1, and 2 on the bottom, or 6/9. And that is 2/3 of 3 is 2 volts. And so the final voltage, V0, is going to just be the contributions of V0 prime plus V0 double prime, which was 4 volts plus 2 volts, or 6 volts total. And that's how you can use superposition. And we'll do at least one more example of superposition tomorrow, and then get more fully into Thevenin and Norton equivalents. So you have all of the stuff that you need to get the homework assignment done. If you have questions, I'll be in my office until, say, 3:30 or 4-ish today. I'll get these notes scanned, but ignore the math on that one with all the dependent sources in it from, but yeah. So if you don't have any questions, let me know. I'll let you know when the exam is where it's going to be, because it will be at 6 o'clock to 7:30 on Thursday night. And homework will be due at the beginning of class tomorrow, which is homework 2. So, any questions? All right, have a good one.